Hi, so today we are using this book. It's a lecture note on analytic geometry and calculus, which is written by Dr. Stephen Moore, a lecturer at the Department of Mathematics, University of Cape Coast. So today we'll be looking at local extrema of functions. When you say local extrema of a function, what does it mean? You look at the definition and some examples. We'll also be looking at increasing and decreasing functions, the first derivative test, concavity, and the second derivative test. So let's begin with the definition of local extrema of function. So look at this diagram, which will help us understand the definition of local extrema. So the graph of the function f of x is bounded between a and b, and we have this point to be L1, L2, L3, and L4. So when we observe the graph, we see that the graph f of x has a maximum turning point at L1, a minimum turning point at L2, maximum turning point at L3, and minimum point at L4. So we say that the point where the graph attains its maximum value is called the local maxima, and the point where the graph obtains its minimum value is the local minima. So looking at the graph, you see that the graph f of x has its maximum value at L1 and L3 and minimum values at L2 and L4. So let's look at the definition of local extrema. So the definition says, let C belong to AB, belong to the interval AB. Then the function f at C has the following extrema. So number one, f of C is a local maxima f of C is a local maxima of f if f of x is less than or equal to f of C for all x belonging to AB. So let's look at this first definition. Say f of C is a local maxima of f if f of x is less than or equal to f of C for all x belonging to AB. So what this means is that when you find C, which is the critical value of f of x, and you find a functional value as f of C, for all x belonging to AB, f of C should be greater than f of x, alright, or greater than or equal to f of x. So this is the meaning of the first definition. And let's look at the second one. The second one says that f of x is a local maximum, it's a local minimum of f if f of x is greater than or equal to f of c for all x belonging to AB. So the second also say that f of x is a minimum of f. So is f of c. F of c is a minimum of f if f of x is greater than or equal to f of c for all x belonging to AB. So when you pick the critical value, you evaluate it and you compare it to the function, you see that f of c will always be less than or equal to the function for all x belonging to AB. Alright, so when this condition is satisfied, we say that f of c is a minimum value of f of x. So let's take the definition of a critical number and how to find the critical number. We have definition, critical number. So we say that a number C in the domain of a function f is a critical number. If either f prime of c is equal to 0 or f prime of c does not exist. So the definition of a critical number is a number c in the domain of a function f is a critical number if either f prime of c equal to 0 or f prime of c does not exist. So one thing you have to note here is that the critical number should always be in the domain of the function given. Alright, then you find f prime of c. F prime of c should be equal to 0 and f prime of c does not exist. So for you to be able to find your c, your critical number, you have to find f prime of x and equate it to 0. Then the x value that you get will give you the c, or will be the critical value for the function. And also you observe the derivative of the function and state at what condition is the derivative not defined. So if you are able to find that value which will make the derivative of the function of x not being defined, then that value which will make it undefined is also a critical number. Alright, so let's take an example for better understanding. So we have an example. It says find the critical numbers of f of x equal to x exponent 1 over 3 multiplying 8 minus x. So this is our question, and we are asked to find the critical numbers. So we use this definition to find the critical numbers. So solution, let's look at our solution over here. So the solution, we will first of all find the derivative of the function. So we have f of x to be equal to x exponent 1 over 3 multiplying 8 minus x. Alright, so we find f prime of x to be equal to here. We can see that there are two functions multiplying, so we resort to the product rule. Alright, so using the product rule, we differentiate the first one. We have 1 over 3 x exponent minus 2 over 3 multiplying 8 minus x plus we keep x exponent 1 over 3. We differentiate 8 minus x, which is give us minus 1. So we simplify this one and we have 8 minus x over 3x exponent 2 over 3 minus x exponent 1 over 3. So when you simplify everything here, we are going to get 8 minus 4x over 3x exponent 2 over 3. So this is what we have for the derivative of f of x. So let's continue. We have f prime of x to be equal to that, and so that for critical values, f prime of x should be equal to 0. Alright? So this implies that 8 minus 4x is equal to 0, because when you bring the denominator 3x exponent 2 over 3, you multiply 2 by the denominator and you have that. Okay, let's take it as our second step. So the second step, we have 8 minus 4x to be equal to 0. So making x the subject, we have x to be equal to 2. Alright? So we also have to look at the second definition of critical numbers. It says that f prime of c does not exist. So we observe our f prime and state the value of x, which will make f prime undefined. So this one is our derivative. So look at it. At what condition is this function not defined? It's undefined when the denominator is equal to 0. So we have 3 x exponent 2 over 3 equal to 0. So here we can see that our x is equal to 0. So therefore the critical values are, the critical numbers of f are 2 and 0. So these are the critical numbers of the function f of x. Alright, it's as simple as that. So now we move to increasing and decreasing functions. You look at the definition and the conditions at which we say that a function f of x is increasing or decreasing. Look at increasing and decreasing functions. So we have that. So here we have to notice that let f be a function that is continuous on a closed interval and differentiable on an open interval. So first of all, the function should be continuous on a closed interval and differentiable on an open interval. Okay, so we have this condition 1. So we have 1 if f prime of x is greater than 0 on, okay, so before, let me write this. I think it's very, very important. So let f let f be continuous on a closed interval AB and differentiable on an open interval AB. Alright. Then we can write 1. If f prime of x is greater than 0 on AB, then f is increasing on AB. And the second one, if f prime of x is less than 0 on AB, then f is decreasing on AB. So this is a definition, or this is a condition for increasing and decreasing function. So we have a function f which is continuous on a closed interval, okay, and also differentiable on an open interval AB. So we say that if f prime of s, you find the derivative of the function and it is greater than 0 on the open interval AB, then we say that f is increasing on the closed interval AB. Alright. If you also find the derivative of the function given and it is less than 0 on the open interval, then we say that f or your function is decreasing on the closed interval AB. So this is the meaning of increasing and decreasing function. So go ahead to look at the first derivative test, of which we are going to make use of these conditions over here. Right? So take note of this one very carefully. We'll be mentioning it very soon. So we look at the first derivative test. And the first derivative test is normally used to find the local maxima and the local minima of a function. So we write the first derivative test. So the first derivative test, we suppose C is a critical number of f, and AB is an open interval containing C. And we also have to suppose further that f is differentiable on AB, except possibly at C. So these are some arguments that we have to make before we state the condition or we give the definition for the first derivative test. So all this must hold, okay, or all these assumptions must hold before we be able to accept what we are coming to write over here. If it doesn't hold, what we'll be writing here becomes illegal. Becomes illegal. So all this must hold. Alright. So number one, we say that if f prime of x is greater than 0 for a less than x less than c, and f prime of x is less than 0 for c less than x less than b, then f of c is a local maximum of f. So what this one means that if f prime of x is greater than 0, what do we say in the increasing and the decreasing of a function? If f prime of x is greater than 0, what do we say? We say that the graph is increasing or the function is increasing. So assuming we have this one, okay, so if f prime of x is greater than 0, the graph will increase. And this one is our a and b. The function is bounded between a and b. Okay, so if we have our critical value to be here, okay, if you have c to be here, and we say that f prime of x greater than 0 for a less than s less than c, so it means this is the interval. Alright, so f prime of x greater than this, it means the function will increase on this interval. Okay, the function will increase from a out to c, and f prime of x is less than 0 for c less than s less than b. So if f prime of s is less than 0, it means the function is decreasing. Okay, it means the function is decreasing. So the function will decrease from c out to b. So decreasing function, it will come down like this. You see. So what we have here is what I've illustrated here. So the interval s greater than a less than b is this one, and f prime of s is greater than 0. So the function will increase from a out to c over here with c exclusive. The values are exclusive. So we come here, and f prime of s is less than 0 for c less than s less than b, and this is the interval. F prime of s is less than 0, so it will decrease. So this sketch or this graph here is a graph which was a maximum turning point. Alright, so you can see this one, a maximum turning point. And whenever there is a maximum turning point, it means the function has a maximum value here. Alright, so the first derivative, this is one condition by which we can say that the function has a maximum value or a local maxima. Let's go to the second one. So the second one is the opposite of what we have written here. So we have 2. If f prime of x is less than 0 for all or for a less than x less than c, and f prime of x is greater than 0 for c less than x less than b, then f of c is a local minima. or local minimum of f. So let's try and illustrate this one also. So we have our graph like this and our extreme values a and b. And let's suppose our critical value is here c. And we say that if, so we consider this interval a less than s less than c. So this is the interval, okay? And if f prime of x is less than 0 on this interval, so we are going to have less than 0 on this interval. It means the function will decrease from increasing and decreasing function that we have seen so far. It means the function will decrease on this interval. And also you say if f prime of s is greater than 0 for s greater than c less than b. So this is that interval over here. So f prime of s greater than 0, it means the function will increase on this interval. So increasing function, we have to increase it here. And when you observe the graph, you see, it means that this value here is a minimum value, or the graph will have a minimum value over here. Okay. So when we evaluate the function at c, it will give us the minimum value of the function. So this is as simple as that. I hope with the sketch you'll be able to remember always. So let's take an example which involves increasing and decreasing of function and also finding local maxima and minima of a function. So we have an example. It's a find the local maxima and the local minima of f if f of x is equal to x exponent 1 over 3 x exponent 1 over 3 multiplying 8 minus x, and also states the intervals over which f is increasing and decreasing. So this is our question. Find the local maxima and the local minimum of f if f of x equals to x exponent 1 over 3 multiplying 8 minus x, full stop, and also state the interval over which f is increasing and decreasing. So we are going to do two different work over here. And we first of all look at finding the local maxima and the local minima. So the solution So what we read so far, in finding the local maxima and the local minima, you need the critical values. Okay, that's the most important thing that will help us to find the local minima and the local maxima. So in our previous example, this is the same question we used in our first example. Okay, and we found f prime of x to be equal to 8 minus 4x over x, 3x exponent 2 over 3. Okay, and we found our critical numbers to be 2, 0, and 2. We have solved for these ones already, so we just have to use them. You don't need to solve again. So we have this information already. So in finding the critical numbers, we just have to write down in finding the local minima and maxima, you just have to write down our f of x. Now f of x is equal to x exponent 1 over 3 multiplying 8 minus x. Okay. So in finding the local minimum and maximum, you just have to evaluate the function at the critical values. So we have f of c, which is 0, to be equal to 0 exponent 1 over 3 times 8 minus 0. So when you finish, you compare the two to see which one is the greatest or the least. So f of 2 is equal to 2 exponent 1 over 3, 8 minus 2. And this one will give us cube root of 2 times 6. And this one, when you evaluate, you're going to get 7.56. Alright. So when you compare the two, you see that the greatest value is 7.56. Okay. So it means that the graph will have a maximum value at s equal to 2, and that value is 7.56, and the graph will have a minimum value minimum value 0, and which occurs at 0. Alright, so we conclude that the local maxima of f, let me write it here properly. It means that the local maxima is 1, so we call it maximum. The local maximum of f is 7.56, and it occurs at s is equal to 2, and the local minimum of 0, and it occurs at s equal to 0. So that's it. So one thing you have to bear in mind in finding the maximum and the minimum value using the first derivative test, you first of all will have to find f prime of x. F prime of x will help you to find your critical value by equating f prime of x to 0. Then you find the solution. Okay, you solve for x. Those values will give you the critical values. And also you observe the nature of your f prime of x to see which condition or which s value will make it undefined. You take that value as also your critical value. When you finish, evaluate the function at those critical values. Okay. When you do it, put the values down and observe the greatest value of all. The greatest value of all will give you your maximum or your local maximum. And the least value of all will give you your local minimum of f of x. Hope it's clear. So let's move ahead to the second part of the question. That is, find the interval on which f is increasing or decreasing. And we know the conditions for increasing and decreasing function. It's like if f prime of s is greater than 0, it means your function is increasing. And if f prime of s is less than 0, it means your function is decreasing. Alright. So we see that we have found the critical values already. And the critical values will help us to write down our interval. Alright. So we have the interval here and so the critical values are 0 and 2. So we can write this interval as from negative infinity to 0 and also from 0 to 2 and from 2 to positive infinity. Alright. So if you want to get it clearly, you can write like this. So your critical values are 0 and 2. So this is your 0 and that is your 2. And you can see that we have three regions. We have this region, that region, and this region. Okay? So this region is from what? Negative infinity to 0. That's what we have here. And this region or this interval is from 0 to 2. That's what we have here. And this interval is from 2 to positive infinity. That's what we have over here. Alright? So let's move on. So we want to look at where the function is increasing on these intervals. So, or where f prime of x is increasing or decreasing on this interval. And we have sine of So we have sine of 8 minus f, sine of 3x exponent 1 over 3, sine of f prime of x, and the direction. Alright, so we have this table. You see these three things we have here, 1, 2, 3, you can combine them as one, depending on your accuracy. So you can, instead of writing this, you can only write sine of f prime of x. And we know your f prime of x to be what? 8 minus 4. 8 minus 4s over, sorry, it's 8 minus 4 over 3s exponent 1 over 3. So you just have to pick any value within this interval, put it into f prime of x and see whether it will give you a positive or a negative value. Then you write the sign, plus or minus. Then you do for this interval, you write plus or minus. You do for this interval and write it. But f prime of x is what? Sorry, here is 8. It's 8 minus 4s. It's 8 minus 4x. Alright. So it's 8 minus 4x over 3x is 1 over 3. So you look at it individually. Okay. So if you find for this one, the sign that you get and over this one, if they have the same sign, it means f prime of x will have the sign of these two. If they have opposite sign, plus negative will give you negative. Then you write minus. So let's look at this interval, minus infinity to 0. So we can see that negative 1 will lie with this interval. You can pick negative 1 or negative 2, negative 3 or whatever. When you put it here, you are going to get 8 minus 4 minus 1. Okay, so you are going to have 8 plus 4, which will give you positive value. Okay, it is 12. So this interval will give us positive. And when you take the same value, negative 1 over here, you are going to get negative 1, negative 1 exponent 1 over 3 times that, and you are going to get positive, and this one, positive, positive will give you positive. And when you pick a value here, which is 1, 1 will fall within this interval. Okay, so when you put 1 here, you are going to get 8 minus 4, which will give you 4. It is positive, so you are going to have plus. When you put 1 here, you are going to get positive. So positive, positive will give you positive. Alright, so here, from 2 to positive infinity, so 3, you can pick 3 from here. So when you put 3 here, you're going to get 8 minus 12, which is negative. 8 minus 12 is what? Negative 4. So this interval will give you negative. And this one, when you put 3 here, I'm going to get a positive value. Okay. So negative, positive here will give you negative. Alright. So the direction is that this one is increasing and this one is increasing and this place is decreasing. Okay. Let me verify something over here. I want to verify something over there. Okay. So when I verified this place, we tested for -1, alright? So when we find the cube root of -1, you are going to get -1, okay? You're going to get -1. You're going to get -1. Let's also test for -2. When you put -2 here, you're going to get, and you put -2 there, you're going to get -1.2599, and I think all of that will give you negative, okay? So we change this positive to negative. So plus negative will give you negative. So here we have decreasing. So we have decreasing over there. Alright. You have decreasing over here. And let's watch something. Let's watch something. So here, we say that we are finding the interval on which L of x is increasing or decreasing. So we are seeing this sign to be downwards. Okay, it means that the function will decrease on this interval, increase on that interval, and decrease on this interval. Okay. So we write that L of x is increasing. L of x is increasing on 0 to and to infinity, and decreasing on minus infinity 0. Alright, so we look at it here and you see that the graph is decreasing here. Okay, the graph is decreasing here. So minus infinity to 0, the graph will decrease. Alright, and here 0 to 2, the graph will increase, and 2 to infinity, the graph will also increase. So these two intervals will give us increasing value. So we have 0 to union, like we bring the union sign, and to infinity. So we will combine the two intervals and then that one alone. So these are the intervals on which the function is increasing or decreasing. So here, when we get to the second derivative test, you can also use it to check for concavity over there. Alright? you check for intervals over there, and it will help to confirm what we have done over there. Okay, so now we have to move to absolute minima and absolute maxima of a function. When we say absolute minima or absolute maxima of a function, what does it mean? It's very similar to that of the local extrema, with the exception that for absolute extrema, you have to involve the boundaries. Okay, you have to involve the extreme values. So you find for all of them, you evaluate all those values plus the critical numbers, then you compare and see which one is the greatest and which one is the smallest. So let's look at absolute extrema or absolute minima and absolute maxima. And it is also called extrema on a closed interval. Extrema on a closed interval. So let's look at the definition. So we let a function f be defined on an interval I, and let's see be a number in I, and let's see be a number in I. So that if you are able to make this argument, then we can write the following. So 1, f of c is the minimum value of f on I if f of x is less than or equal to f of c. As I said earlier, this is similar to the local extrema. For every x or for every x in I. And we have the second one. We have the second one. It says that f of c is the minimum value f of c is the minimum value of f on I if f of x is greater than or equal to f of c for every x in I. So f of c is the minimum value of f on I if f of s is less than or equal to f of c for every x in I. So this I is the interval Okay, is the interval of the function, or is defined on the interval on which the function is defined. Here the interval, we change it, is I because actually we consider the extreme values, or the interval is to be part of the domain. Okay, so we have this interval, and we have to find C for the critical values and also the extreme values on the interval. We evaluate all of them, then we see the greatest one, and we pick that one as our absolute maxima or absolute minima. So we'll be looking at the steps involved in finding absolute extrema of a function. So let's look at the steps involved. Let's look at the steps. So, steps for finding absolute extrema. Steps for finding absolute extrema. 1. Find all the critical values. Find all the critical values of f. Then 2. Calculate f of c. Calculate f of c for each critical number. And 3, calculate f of a. So let me write the 3 here. Let me write the 3 here. The 3 says you should calculate f of a and f of b, which are the extreme values. 3, calculate f of a and f of b. Then 4, which is the last step, the absolute maximum and minima. The absolute maxima or minima the absolute maximum or minimum of f on AB are the largest and smallest of the functional values are the largest and smallest of the functional values calculated in step 2 and step 3. So this is how to find absolute extrema. You first of all have to find the critical numbers, or find all the critical numbers of f, which is 1. You calculate f of c. You find the functional values of those critical numbers. That is 2. And 3, you calculate f of a and f of b. That's the functional values at a and b, the extreme values. And also, the third step, you have to observe all those that you have calculated in step 2 and 3. Then the greatest of all is your absolute maxima, and the least of all is your absolute minima. Alright, so let's take an example over here to better our understanding of what we have said so far. So we have an example here. Say if f of x is equal to s cubed minus 12x, find the absolute maxima and absolute minima values of f. So let me change the maximum and the minimum to maximum, minimum values of f on the closed interval minus 3 and 5. Right, so this is a question that we have. If f of x is equal to s cubed minus 12x, find the absolute maximum. Say, what is this? Find the absolute maximum and absolute minimum values of f on the closed interval minus 3, 5. So one thing you have to know about local extrema and absolute extrema is that, okay, the difference is that for absolute extrema, you have to include the extreme values, that's a and b. You find the functional values at a and b. And also, the absolute extrema, you will always be given an interval, okay? You'll be given an interval, that's your a and b, okay, to be included in finding your functional values. So two things, absolute extrema, you have to include the extreme values, and also you will be given an interval. So this interval here, it is your a and b. Okay, for local extrema, there's no need for us to be given, or there's no need for a and b. Okay, but for absolute, you will always be given the closed interval. So you include this one in finding your functional values. So let's look at the solution of this. So solution, we have f of x to be equal to s cubed minus 12x. So remember that here we need our critical values, okay? So you have to find the critical values from here, and finding the critical values, you have to differentiate the given function. So you have 3s squared minus 12. And for critical values, we say that f prime of x to be equal to 0, okay? So if you are writing the question, I'm giving you 30 seconds to finish writing the question, so that I can claim this place. Okay, I believe you are done. You are done. So let's continue. So it said f prime of x will be equal to 0, which will imply that this will imply 3s squared minus 12 is equal to 0. So we find for x, and we have s is equal to 12 over 3, which is equal to 4. And we have our s to be equal to square root of 4. And square root of 4 is plus or minus 2. So we have our critical number to be plus or minus 2. Okay. So we again have to, when you get your critical numbers, we are not done. We make exercise from, we are not done. So you go back to your f prime of x to see at what condition is the function or your f prime of x not defined. So you look at it and you see that this function here is a polynomial. And you see that polynomial are functions, there are special types of functions which are defined throughout their domain. Okay, so there is no instance that this polynomial will be undefined. So our critical numbers are solely plus 2 and minus 2. So critical numbers are two and minus 2. So now that we have our critical numbers, we have to evaluate them. That's step 2. This is step 1 that we have done. So step 2, we evaluate them, or we find the functional values at 2 and minus 2. So we are going to step 2. So we find f of 2 to be equal to, so this is our f. So we get 2 exponent 3 minus 12 times 2. And this one will give us, please let me write it nicely over here. Alright. So we are finding f of 2, and we are going to get 2 exponent 3 minus 2 exponent 3 minus 12 times 2. Alright. So we are going to get 8 minus 24, and this one will give us, minus 16. Yes. Alright, so we find f of minus 2 and get minus 2 exponent 3 equal to 12 minus 2. And this one will give us minus 8 plus 24, and we are going to get 16. This is step 2. And step 3 also says that we should find the functional values at a and b. And our a is minus 3, and our b is 5. So we find f of minus 3 f of minus 3, and we have minus 3 cubed minus 12 minus 3, and this gives us minus 27 plus 36, and this one will give us 9. And we have f of 5, and we have 5 cubed minus 12 minus 5, and this one will give us 65. Okay, so this is our third step, and our fourth step says that we should compare all that we have done, our results in 2 and 3, to see which one will give us our greatest value. The greatest value is the absolute maximum, and the least value is the absolute minimum. So we compare all, and we see that 65 is the greatest and minus 16 is the least. Alright, so let's write thus the absolute maximum is f of 5, which is equal to 65, and the absolute minimum the absolute minimum is f of 2, which is equal to minus 16. Alright. So that's what we have over there. So this ends absolute extrema. So we will be looking at concavity of a function, concavity and the second derivative test. So concavity and the second derivative test, we all have to, or it's all about where the function will have a maximum and a minimum value, and also it gives us an idea of where the function is increasing and decreasing. Okay, and it also enables us to sketch the graph. When you are told to sketch the graph of the function, it will enable us to sketch the graph appropriately. Alright, so concavity and the second derivative test will see us in our second video. So see you in my second video. Thanks for your time, and don't forget to subscribe to my YouTube channel, Think Math, Think Further Noah, for an update on